So exam stuff, I'm going to try to get to grading the exam in between the mountain of stuff we have to do to get ready for our ABET visit, which is starting this Sunday. So my guess is probably Sunday after I give them the tour and have to sit around for a while waiting for a meeting. I will get a lot of grading done then. So figure next week sometime. Yeah. I appreciate the thought. I'll keep that in mind. Monday is, yeah. Appreciate that too. But Monday we're looking at probably not having class because I've got meetings, ABET meetings that are right on top of that. Yeah. It'll just be due sometime Monday. Just throw it in sometime Monday. So thanks for asking. All right. So along those lines, so that you can do homework, we need to learn some things. And we're going to finish up this DOE 3 group problem that we were working on before. Essentially, we had two situations. First one where we took a set of data and what could have been used as a blocking variable, we said, let's just ignore that blocking happened and treat this experimental design as two replicates. Right? So we went through and we got E star and SE and figured out the main effects of X1 and X2 were important, but the interaction effects were not significant. So now let's take the same data set and introduce the blocking variable, which is really how we set the experiment up anyway. And now we're going to do the same thing as far as let's figure out what is significant, what is not significant. But we get SE a different way. You'll have to go through your brain or read through your notes to figure that out. But let's work on this. Analyze these data, this experimental design, where we have this blocking variable X3. So go ahead, get in your groups, and let's see how fast we can get this done. Yeah, Matt. Okay. Yeah, go ahead. Okay. M is just the number of these VIs that you added up. So however many blocking interactions you use to calculate the numerator, that's the number that is in the denominator. So I was just going to refer back to that. So you identified those 3, and so M is 3. Yep. Yes. Yep. They're still a reflection of the noise, right? So you have 3 data points, 2 of them just happen to be 0. Kendall, you're all alone in the group problem now. So, yeah. Yes. This is the staging ground for leaving the class. Yeah. Question? Right. Right. It's gonna cost you, yeah, degrees of freedom to introduce a blocking variable. That's right. Yeah.
So when we're defining SE squared
Mhm.
from the blocking reactions,
Yep.
we just divide by the number of nodes. It's just an average
Yes.
out. Okay.
Yep. Yeah. So it's the case where we're just calculating the standard deviation of those numbers, but in this case, we know the mean. We know mu at 0 by assumption.
You is that big? Just get big.
So I always ask how many degrees of freedom went into your calculation of your noise. So so always look at, how did you calculate this noise? It's standard deviation always, or variance is sum of squares divided by degrees of freedom. Yep. Yeah. Sean.
The effects are blocking variable when we're calculating SE.
No, the blocking variable very well could be big. That's why we're doing it, because we think the effect of X-ray is going to be big. But it's the block factor interactions that we assume are just a reflection of noise.
Okay, just wanted to make sure.
Yep, good question. All right, so it looks like I've looked around. Most people are down the path of I need SE, which is the noise of the effects. And to do that, you need to identify the blocking interactions, which are the interactions between factors and blocking variables. Factor, blocking variable, factor. So, did you identify those three effects as the blocking factor interactions? Good. So then these effects are just a reflection of noise, right? So we're going to take all of these guys, calculate the standard deviation of those three numbers with the assumed mean of 0, and then that will be the noise in the effects themselves, not the individual measurements, but the effects, because those three numbers represent effects. So we have, right. So the question was, this is the second time this came up. This effect right here, think about this. This is the effect of our blocking variable. And we have a blocking variable because we think this is something big that's a source of error that's going to mess up our experiments. So if we think this is big and real, we're not going to lump it into the noise. Right? The whole purpose of this is try to remove this guy from the noise. So the only way, our assumption is that the factors don't interact with this blocking variable. Or said another way, that the effects of the factors have to be much, much bigger than these blocking interactions. So that, remember the equation that we're using for standard deviation is numbers minus mu divided by n in general terms, right? So when you know mu, you divide by n, not n minus 1. Remember? So we've assumed mu is 0. So we're saying we know it. We're saying it's 0 by assumption, and that's why we divide by 3 instead of 2. Pardon? So our assumption is the mu of the blocking interaction effects is 0. Yes, and that's always going to be our assumption in these block designs. So SE turns out to be that. How many degrees of freedom? We got to get a T star. How many degrees of freedom does it have? I heard some 3, some 4. Always ask yourself, when I'm going to look up my degrees of freedom for T star, how many degrees of freedom went into the noise? So we have 3 degrees of freedom there, right? 3 degrees of freedom. I got T stars 3.182. And we find everyone okay with what we've done so far? Did you guys get that far? Good. Let's compare these two things. One thing we could compare would be our hurdle value for effects. In the block design, it went down, right? So that means the precision of the experiment went up. If you think about this in terms of power, this design would have a higher power than this design. We can detect smaller and smaller effects. They'll show up as significant. So think of E star. It's the product of T star and SE. When we went from unblocked to blocked, what happened to T star? So compare T star here to T star here. It went up. Why did it go up? Less degrees of freedom. We went from 4 degrees of freedom here to 3 degrees of freedom in that guy. So T star went up, but obviously SE went down significantly, right? So blocking, when we block an experiment, we burn up degrees of freedom, so our T stars are going to increase, but we're hoping that if the blocking's effective, that the noise is going to go down more than enough to offset the increase in T star. And so you'll see lots of questions, was blocking effective, right? And so that's what they're getting at. One way to do it is to compare these E stars. Another simple way would be, does the block effect show up to be above our hurdle value? It's another way to get at blocking seems to be doing something helpful for us. So in this case, we would say blocking was effective. It's a good thing that we did that. We reduced the noise in our experiment. And one practical thing is we determined that this X1, X2 interaction is real. And if we wouldn't have blocked it, we would have missed it. Right? In this design, we didn't say X1, X2 interaction was real. What happened is we missed it because our noise was so great. The power of this experimental design was lower than this one. So even though X1, X2 was doing something, as we found out here, it was swamped by the extra noise in the top experiment. Does everyone get that? Okay, so let's do something fun, as if this stuff isn't fun enough already. So that's fun as well. Yeah.
What does this new E-star tell us about the effect of the block?
I'm sorry, I can't hear you.
What does E-star tell us about the effect of the block?
What does E-star tell us about the effect of the block? Block effect is greater than E-star, so we would say it's significant, which means the effect of that blocking variable is discernible from noise. So it really is having an effect. Okay. Now, let's think about one thing. Notice one curious thing in these two experiments. Notice the effects when we did analyze this different ways. Notice the values of these effects didn't change. That might not be too surprising. But let's look at doing something to talk about one of these important properties of this design. So what I'm going to do is I'm going to go in here, I'm going to change a bunch of data, and we're going to think about how that will affect the calculation of our results. So I'm just going to pick a column, this one, just because it's close by and I can not lose my place in the rows. But every one time there's a -1, I'll subtract something like 10 from the result. Every time there's a +1, I'll just add 10. So I'm just going to mess with all the data. So if I did that, and what did I say? I'm going to subtract 1. Okay. So I just changed the whole data set. And now I want us to redo the problem as far as calculating the effects. We could race. In years past, I've raced the whole class, but I'm already done, so it's not really fair. Okay? So let's think about how, let's do the easy one first. This new data set, what's that effect going to be? Let's go based on what we got before and how we changed it. Every time there's a -1 here, I subtracted 10, +1, I added 10. So what's going to happen to the effect? The average, what's it going to be? All the high values are going to have 10 more. All the low values are going to have 10 less. 20. Average of the high values minus the average of the low values, or 4 estimates of low to high. Does everyone see that? Okay, that was the easy one. The other one is a little, what's going to happen to these? All right, how many do you have? 6. All right, so why don't each row take one of these? You guys do this X2, X3 interaction. You guys behind do the X1, X3 interaction. You guys in the back, X1, X2. Right here, main effect of X3. You guys in that second row, X2. Back row there, X1. And then let's just keep going. Kendall, your row. Let's do this again. You confirm this one. And then back there, you guys do this one again. And then way in the back, you guys do X1, X3 again. So recalculate just the effect assigned to your row. It's not that the noise bothers me, it's just that I don't want it to be drafty. There's too much ventilation in the room. So that's nicer. It's calmer, cozier. All right, so the new data set, 20. Tell me when you're done. All right, you guys are done. What'd you get?
0.
You got 0. You guys got -1. You guys. -4. Up here. Go, come on. What'd you get?
3.
Got a 3. What'd you guys? 6. 10. What'd your group get, Kendall? 20. Good. All right. 0. -1. All right. This is good. What group messed up?
It shouldn't change, it looks like, but if you actually plug in the numbers.
All right. We have everybody do this one. It's the class against the front row. It shouldn't.
But if you like plug in the numbers.
It still shouldn't. Uh-oh. Did we get 3? Wow. Did we not do something right? Maybe this was 3 all along. Ooh, why don't we do that? Why don't we do this? That'll be fun. It was 3 all along. Nice. Okay, good. We've resolved the conflict. So it's probably the printer's fault. Sometimes it prints 4s as 3s, if you guys have noticed. All right, so the good news is what happened, right? None of the effects changed. Does it surprise you? I just changed every data point. So what does that mean? Let's think about what that means. Aiden. Okay, thanks for that. I don't think student pencils are the same as it's trickier to do printing. But so I hope your skills are better than your printing skills. Let's just say that. All right. So none of the effects changed, right? And we changed all the data points. What that means, if we think about practically speaking, you can't just arbitrarily change data, but I changed it in a very specific way. I changed it according to this column. So what that means for us is each of these columns, or the columns, are orthogonal with each other. Good. All right. So we have orthogonal columns, which means the dot product of this column with any other one is 0. You take any 2 of these if you think of these as vectors, and you dot them together, you get 0, right? That's what you learned in statics and other classes like that when you dealt with vectors. So that means it'll be really important to us coming up here pretty soon. That means that the effect, this effect right here doesn't impact any of the calculation of any other effects, right? So example, whatever x2 is doing, we can calculate a big effect for x2, a small effect for x2. The other effects aren't affected by that. If I wanted to just get rid of this column completely and reanalyze the data, none of the effects would change. So we're going to use that coming up very soon when we look at at trying to build a model that only has significant effects. And if you think about this, we didn't even think about this too much when we were building a model. Remember when we had y hat and we had all the b's and those sorts of things? When we went from, there's the model we could have had, all those effects divided by 2, but when we put in only these significant factors, we didn't ask ourselves, if I drop these terms from my model, do these effects change? So here we've kind of proven it to ourselves that it was okay what we did before, that we can just look and say, well, which effects are significant? We're just going to include those in our model. We're going to drop all the other terms. So this idea of orthogonality is going to be really important when we get into model reduction, and in the end of the class, we're going to look at designs that are not quite orthogonal, and it's going to be a lot more tricky. It's a lot trickier to get that model. All right, any questions on that? Okay, so that's one of the very nice, unique features of the orthogonal designs. Said another way is, when you calculated the effects at the bottom of this column, they were perfectly balanced, where they had plus 10 and minus 10 that seemed to cancel out on the low and high side of those values. All right. Well, let's skip over split plot designs and move to the next section of the notes, DOE 4. So now we're going to move very quickly away from all this, well, not away from this full factorial design, but all the stuff that we learned in full factorials is going to be the basis for what we study from here on out. So if you have some holes in your understanding of full factorials, please take the time to fill those in, because we're just going to be building on that stuff from here on out. So I think I'm going to go PowerPoint for a while. All right, I'll let you read through that. It is amazing how many times Dilbert seems to be right on the money. It was pretty funny when I had a real job a long time ago, and I worked at Koch Engineering, and we had an engineering group meeting, and the whole purpose of the meeting was, how can we be more efficient? And we went to this meeting, and it ended up being, well, no one really wanted to say the really hard things about how we can be more efficient, so we all settled on, let's get new, faster computers. And then the next week, that exact thing came out in a Dilbert cartoon. And so everyone had it posted on our door, and it was pretty funny. So anyway. And it'll probably happen to you too. So, all right. So we've been talking about full factorial designs, right? So these are 2 to the k designs. And if we just look at, all right, how many factors do we have, and how many experiments do we have just for a single replicate? All right, we've been looking at 4, 8, 16, 32 runs. But as the number of factors increases, these numbers get hard and impossible to manage, right? That's a lot of experiments when you're dealing with a lot of factors. So that's the problem. Our full factorial experiments, they're not going to get us to this point of we can manage a lot of factors at once. So what we need is some method, if we have a lot of factors, how do we efficiently test all those factors, throw out the ones that aren't doing anything, and then take a smaller set and drop them into what we've just been doing with full factorials and go from there. So this would be the first step that happens before the full factorial step. This is the step before what we just learned. And our goal here, how do we reduce the number of factors? So said another way, If we think about the number of factors, okay, same sort of column as before, whoops. And the number of runs, again, same as before. Let's think about one thing that we said before about interactions, is we said just from practical experience, main effects are very often important. Two-way interactions are very often significant, some of them. Those are the two things that we really want to find out from our experiment. We want to test the main effects and the two-way interactions. But do you remember what we said about higher order interactions? We said it just fairly briefly a couple of times. We said three-way interactions, four-way, five-way. Those are almost always just noise. Higher order interactions are very, very rare. Remember we had that one example where a three-way interaction showed to be significant, and I said don't let this mislead you because this is very rare. So let's think about that concept in this table right now. So if that's true, which it is, we want to build a model that's going to have, well, the mean, it's going to have main effects, and it's going to have some two-way interactions. But we don't want to burn up a whole bunch of degrees of freedom to estimate the coefficients for three-way, four-way, five-way interactions, right? Because they're going to be noise anyway. So what this is getting at is, these are the number of runs I'm doing. How many degrees of freedom is it going to take to calculate a mean? Well, it's going to take 1. How many degrees of freedom will I have to use up to calculate the number of main effects? Well, you're going to have to take 1 degree of freedom for each factor. How many two-way interactions? And you do 4 choose 2, 5 choose 2, and so forth. So then if we add up these, 7 degrees of freedom we're using to calculate important things, and 1 degree of freedom is, in this case, 1 degree of freedom is going to be used to calculate that three-way interaction. So this is a pretty efficient design. So 88% of our experiments go into calculating important things. As we increase factors, and we do that again, we add these numbers, 11 out of 16, that's only 69%, still pretty good. And this number drops off rapidly. So if we get down here, if we have 9 factors, less than 10% of our experiments are going into calculating the important things. And all the rest of the degrees of freedom, and there's a lot of them, are going into calculating things we know aren't going to mean anything, that are just noise. So the rest of the degrees of freedom here, 91% of the degrees of freedom of these 512 runs are just going to help us get a handle on the noise. That's a lot of degrees of freedom to just get a handle on noise. Way too many degrees of freedom. So what we're looking at doing is, how do we drop this down and keep all of these percentages fairly high so that we're doing a reasonable number of experiments to calculate important things, which means the effects or the coefficients of the main effects and the two-way interactions and the mean. And then leave left over a reasonable number of degrees of freedom to estimate the noise. Okay, that's what we're going to do. Everyone okay conceptually? That's our goal. And as efficiently as possible, knock those large number of variables down to some reasonable subset that we want to study further. So we've presented this before. This is what we learned and had an exam over, and this is what we're learning now. So we're backing up. This is the first thing that you'll do when you don't know a whole lot about what you're studying. You have a big laundry list of factors that you think might be important, and you're going to say, how do I very efficiently chop that number down from, say, 20 to 3, 4, 5? So that means, I'm not going to talk about that. That means we have to reduce the number of experiments somehow. Right? So we think about, let's just look at this. Let's say we have this full factorial in 4 factors, And in this case, even 16 runs seems to be too many. So we're not going to run a full factorial. This whole section of notes is we're not running the full factorial. We're running less than that. So we need to take out some experiments. And so here, if we just say, let's just take out these experiments. So I just pick these 4, pick those 4, they go away, and we're left with this. So now we've reduced the number of experiments in half. We went from 16 experiments down to 8. So now let's think about what have we done? All right, so remember we've got numbers here for y. Think about calculating the effects at the bottom of those columns. Does anything seem problematic when you're going to calculate the effects? You can get numbers, but compare the effects you're going to calculate. Anyone see something? Yeah, John. Yes. Anyone else see that? When you calculate a number for the effect of x2, you're going to get the exact same number for the effect of x3, right? So that's going to be hard to interpret. Another way of saying this, when we changed x2, we changed x3 the same way. So think about this. If you take 2 variables and you change them the same way every time in your experiment, they're both low, they're both high, they're both low, they're both high. Have you studied them independent from one another? No. So whatever number you're going to calculate here, let's say it's 20, that's going to be the combined effect of whatever x2 was doing and whatever x3 was doing. So we'll buy that. Because they changed exactly the same in our experiments, that number, E2 and E3, it's the same number, is the combined effect of whatever x2 is really doing and whatever x3 is really doing. Yeah, fine.
Is that different from the interaction between the two?
That is, yes, it's not the same as the interaction. What we say, we would say x2 and x3 are confounded. It's a good word. They're lumped together. We can't separate them. They have not been studied independently or apart from one another. Does that mean that the effect of x2 is the same as the real effect of x3? No. It just means we can't separate whatever those 2 real effects are. So that's bad, right? So that's how we'd calculate those 2 effects. It's exactly the same in both cases. It's just what I just said. So now the problem is, whenever we take a full factorial and we reduce the number of runs, we are going to get confounding. It has to happen. So we're stuck with that. We're stuck with this unhappy situation, is we're going to have things confounded together. Now let's just think of the things that we're going to calculate. We're going to calculate main effects. We're going to calculate 2-way interactions. And then we're going to calculate 3-way, 4-way. I'll call them higher order interactions. Yeah, Thomas.
So we decided which ones to take out?
I just picked them randomly. Actually, I picked them from the guy who made these slides that I took. So he did it. All right, but for us, we just picked them. Now, what I'm saying is, let's say you have a 2 to the 4th, a 2 to the 5th design. You're going to calculate these things. We know confounding is going to happen, right? So the best thing, the only thing that we can do is manage it the best way we can. So think about, how are we going to manage the confounding? If you could pick the confounding, what would you do? Here, this is the worst case. We confounded main effects with each other. That's bad, right? We have main effects. We have 2 different variables, x2 and x3, and we haven't studied them independently. So these are two really important things. They ended up being confounded together. We don't like that. What would you like to, if you have to confound something, what would be the best way to manage it? What's that? The higher order interactions with what? With each other? So a three-way interaction with a three-way interaction? What about these guys, the main effects and two-way interactions? They have to be confounded with something as well, right? Every effect will be confounded with something else. We can't have it clear, have main effects unconfounded. So I should have specified that. But you're on the right track. Yes. What Aiden is saying is these guys are important, right? They really could be doing something. These guys are almost always just noise. So if we are stuck with confounding, what we really ought to try to do is set about managing this confounding so the important things are hopefully only confounded with the unimportant things. So when I confound the main effect of, say, x4 with a four-way interaction, and I calculate that effect, I'll say, okay, that effect represents the main effect of x4 plus whatever that four-way interaction is doing. Well, we'll assume the four-way interaction isn't doing anything, and we'll have a pretty good idea of what the main effect of x4 is. I said that was a big, long sentence, a lot of words there. We'll look at that in example form a couple times. But conceptually, did everyone see that? That's what we're going to do. Our job in this section is all about this. It's going to take us a long time to get through it, but we're going to try to figure out what are the best ways to manage the confounding as best we can. So, let's see here. All right, so this is just... So how do we do it? And I might go down to the notes now and get out of this PowerPoint slide presentation. So what is the way that we can confound or manage the confounding? So, well, I guess there's one more PowerPoint worth. So how we do that is we figure out how many runs are we going to do, 8 or 16 or 32, and however many runs we do, let's just write out the computation for a full factorial in that number of runs. So in this example, we said we're going to do 8 runs. So in this example, we want to study 4 factors in 8 runs. This is what we're trying to do. If we wanted to study 4 factors for a full factorial, how many experiments would we need? 2 to the 4 is 16. We're running half that number, right? So this is called a half fractional factorial design. Right, so we're running half of what a full factorial would require. The procedure is, okay, take your number of runs, 8 runs, and just build the full computation table. 8 runs would be a full factorial in 3 factors. So that's what I have there. Is everyone okay with that? That's a full factorial for 8 runs. So now we can do this, and we can study x1, x2, x3 just fine, but we don't study x4 is missing right now. So what we're going to do is we're going to add that in. And what we're going to do is when we add this in, think about what we need, what we're doing. When we're adding x4, in these 8 runs, we have to assign high and low values to x4, right? So for this run, we're running the low values for x1, x2, x3. Somehow we have to set x4 in there as well, right? So how do we set it to minimize the confounding? What we do is we take x4 and we assign it to one of these columns, and by doing so, we have deliberately confounded the x4 effect with whatever column we assign. So if I say here, if I say x1, x3, if I say these are the settings that I'm going to use for x4, then I've confounded x4 with this two-way interaction. So x4 is a main effect. What would you want to confound it with in this situation? Which column? Yeah. Right. So we would want x4 to be confounded with this three-way interaction.
Do you ever go through and find the effects and then assign it based on whether that's relevant?
Oh, great question. This is going to help us understand what's happening. Then we're going to get a shorthand method for doing this assigning. But this is sort of the long way about it, so we understand it. So these are the settings then. These are the settings of x4. So when we do the experiment, right, that highlighted box, that's the experiment. So that highlighted box just condensed those. This is the experimental table that we did. That's what we're going to go run x1, x2, x3, and x4 in. And we're going to get data in 8 runs. And we know one thing. We know x4 is confounded with the x1, x2, x3 interaction. But we have confounded other things as well. If we think about in a 2 to the 4th experiment, you can calculate 16 things, 15 effects and a mean. If we only have 8 experiments, right, and we're going to calculate 16 things, our confounding is going to happen in groups of 2. So x1 or x4 is confounded with something, x3 is confounded with one thing, and same with x2 and x1. The two-way interactions, each of those is confounded with another thing. We need to figure out, and this will be the last thing we'll talk about, if we take that and I expand that out in the full computation table, we already determined x4 and those two things are confounded, right? You see how that column is the same as that? Take a minute and start figuring out other things. What's the mean confounded with? The four-way interaction. What's x1 confounded with? 2, 3, 4. You see the symmetry happening there? Okay. I missed that. There it is. I drew it perfectly straight. That's really nice. All right. So there's symmetry happening there. The 1, 4 interaction and the 2, 3 interaction are confounded, right? And so forth. So if we wanted to summarize this design, we'd say main effects are confounded with three-way interactions. Two-way interactions are confounded with each other. So one thing that's good, main effects are confounded with three-way interactions. That's great. Then we're pretty confident in our calculation of main effects. The two-way interactions confounded with each other, that's not so great. It's not horrible, but it's not so great. But those are designs that we sometimes live with. So the confounding happened in pairs, and the only thing that we can do is manage it as best we can. So we are 1 minute over. Wow, but it was a fun minute, right? We had a good time. So see you Friday.